All right, let's look at Vvm graphs, where we model the momentum of objects in a collision using velocity versus mass graphs. Let's go. So a Vvm graph, all it is, it's a graphical model of momentum. It's a way to visualize an object's momentum. We put velocity on the y-axis, mass on the x-axis, and that's all there really is to it. But let's recall that momentum is a quantity describing the mass and velocity of an object. P, momentum, equals mass times velocity. Memorize that. Momentum can be used to analyze and predict the results of collisions and explosions. That's why physicists like them so much. So here's a collision. It's on a simulation. And this collision is an elastic collision. You can see down here, it's an elastic collision. It's set to elastic. And this one's perfectly elastic. That means there's no sticking together at all. The first thing we do when we're drawing our Vvm graphs is we analyze the initial conditions. And so look at the initial conditions. We have the red cart and the blue cart, and we can see their mass, and we can see their initial velocities there. And that's what we want to collect as data. Initial just means before they collide, before the collision. And we're going to collect data. We can write those numbers down somewhere. And then the next thing we do is we throw those numbers on our graph. Here's our Vvm graph, and we're going to add our initial conditions there. Just like that. It looks like that. So if you look closely, you can see that this is for the red cart. This is for the red cart. And I'm looking at the y-axis. There's its initial velocity of 1. And I'm looking at the x-axis now. There's its initial mass of 2 kilograms. And it's all there. The area represents the momentum. That's why we fill in this little space right there, because those 2 blocks, that's how much momentum the red cart has before it collides. So there it is. The area represents the momentum. Remember, P is momentum. That little I is initial, and this is the red cart. So we're labeling things. Next thing we do is we analyze the initial conditions for the other object. There's the blue cart, and it has a negative velocity, so that's why that one looks different. The same thing, we have the initial momentum visualized in this graph by looking at the area. It's got negative 12 kilograms meters per second of momentum. And that checks out if you do the math. P equals m times v. The numbers work that way too. You can do the formula or you can look at the graph. Now, the last thing, look at the final conditions. Look at the final conditions. Here we have the mass doesn't change, but it looks like the red cart shoots off to the left with negative 5 meters per second of velocity, and the blue cart comes to rest in this collision, in this inelastic collision. Final just means after the collision. So we'll write down the data somewhere. And we're going to draw our graphs the same way that we did before, and they look like that. Easy peasy, lemon squeezy. Now, what you want to do is you want to analyze some patterns. You want to look at the area or the total momentum of each object. So look at the total momentum of each object, the initial and the final. But what might strike us as kind of cool is when we look at the pattern of what happened of the total momentum before and the total momentum afterwards, which is kind of cool. You'll notice that plus 2 minus 12, if we combine those numbers, we get negative 10. And that's how much total we have down here. So that's an interesting pattern. And that tells us that the total initial momentum of the system equals the total final momentum of the system. And those numbers just show what I just showed before. Positive 2 plus a negative 12 equals a negative 10 plus 0. And we end up with, negative 10 equals a negative 10. Now, it's important to know what move my head here. I'm being blocked. All right, I'm getting rid of my head. It's important to know what an inelastic collision is. Now I've set my settings to inelastic, and this just means that the carts stick together when they collide with one another. Inelastic means the objects stick together, and this one's perfectly elastic. There's no bouncing apart at all. And we set it up the same way, especially before. We have the same setup before the collision, but after it's a little different. And let me show you what you would do. You would do this. You would set up I'm using purple because red and blue together is purple. And I'm treating these objects as one object because they're moving together. I just added their mass. So their total mass is 5 kilograms and they're moving together at -2 meters per second. And then I drew them on one velocity versus mass graph. And that's all I do for an inelastic collision. Now I'll leave you with this. Recall that I can't seem to move my, whoa, now I'm huge. Okay, nope. All right, getting rid of me. Recall that an object in a collision will experience a change in momentum. But the system's momentum will not change if there are no net external forces on the system. So the initial momentum of the system will equal the final momentum of the system. That's a big idea called the law of conservation of momentum. And those velocity versus mass graphs are the perfect way to visualize it. You guys got this. Good luck.